Okay, so we have almost completed diode circuits, and this is the last part actually. So I would just call it class 14.1 because it's a 15 minutes class basically. So let us consider a diode circuit like this. So we have V1 here, two voltage sources V1 and V2, and then we have diode, and these two diodes are actually connected to a resistor R, and we take the output voltage from here, V0. So we have actually done a problem like this earlier, and this is not a problem, but this is mainly a circuit analysis which we are going to do today. So let us consider that V1 is 5 volts and V2 is 0 volts. Okay, so we'll make a table here, V1, V2 and V0. It's actually difficult to draw straight lines, but anyway. So let us consider that V1 is 5 volts and V2 is 0 volts. Okay, so immediately from our previous experience, we know that if V1 is 5 volts, here this is 5 volts and this is 0 volts over here, then we immediately know, because this voltage is 0 volts and this voltage is also tied to the ground, we immediately know that this diode, let us call it D1 and D2. So we immediately know that D1 should actually be forward biased. Okay, because V1 basically is 5 volts, V2 is 0 volts, and this point is grounded, so D1 must be forward biased. And we also know from our previous experience of on problems like this that D2 is actually reverse biased in this case. Okay, uh, because V2 is basically 0 volts, and since we have a resistor R here, if D1 is forward biased, then the current must flow through this path, and so this point must have a voltage which is greater than 0 volts. Okay, and because V2 is 0 volts, this diode D2 must be reverse biased. Okay, so in this case, if V1 is 5 volts and V2 is 0 volts, then this diode D1 is forward biased and D2 is reverse biased. And then, because in the forward bias state of this diode, uh, a voltage V gamma would drop across it. So the voltage drop across it would be V gamma. Okay, so since we have 5 volts over here, the voltage at this point must be equal to 5 volts minus V gamma, which is basically 4.3 volts, assuming that V gamma is 0.7 volts. So let us assume that V gamma is 0.7 volts here. Okay, so the potential at V0, the voltage is 4.3 volts. Okay, now let us assume another situation where both V1 and V2 are at 0 volts. Okay, so both V1 and V2 is basically at 0 volts. So 0 volts here and 0 volts here. Now if both V1 and V2 are at 0 volts, then if we put 0 volts here and if we also put 0 volts here, and this point is grounded, so basically all the points in this circuit are at 0 volts. So basically no current flows to the circuit, and if no current flows to the circuit, then this voltage at this point V0 would be equal to 0 volts. Okay, because basically no current flows through this resistor, so there is no potential drop across this resistor, so V0 must be equal to 0 volts. Okay, so we write 0 volts over here. Next, there can be another condition that V1 is basically 0 volts and V2 is equal to 5 volts. So V1 is 0 volts and V2 is 5 volts here. In this case, see, this is the actually exactly I would not say opposite, but we have basically interchanged the nodes V1 and V2. Okay, so this case 0 volts and 5 volts, this case is basically the same as this case. Only the thing is that we have interchanged these nodes for V1 and V2, and since the arrangement is actually symmetrical with respect to V1 and V2, the output here would also be 4.3 volts. And if you want to look at it in a little bit more detail, when V2 is 5 volts and V1 is 0 volts here, in that case, just like before, this diode D2 would actually be forward biased, and D1 is basically now reverse biased. Okay, and if D2 is forward biased, the voltage drop across D2 is basically V gamma, which is 0.7 volts. So voltage at this node must be equal to 4.3 volts. So that's the explanation for V1 equal to 0 volt and V2 equal to 5 volt. And the fourth case that we might have is basically both V1 and V2 are at 5 volts. So both V1 is at 5 volts and V2 is also at 5 volts here. And in this case, because both V1 and V2 are at 5 volts, this diode D1 and this diode D2 are both are forward biased basically. I mean, there is no reason why one diode should be forward biased and the other should be reverse biased, because we have applied 5 volts to both this node V1 and this node V2 here. Okay, and then if both D1 and D2 are basically forward biased, then the voltage drop across each is equal to V gamma. So V gamma voltage drop across D1 and V gamma voltage drop across D2, and so the voltage at this point is again 5 volts minus V gamma, which is basically 4.3 volts. Okay, so we have 5 volts, 5 volts, and the output V0 is basically 4.3 volts here. Okay, now if we consider that for, let us say, V greater than 2.5 volts, we would consider this to be logic high, and V0, so V0 less than equal to 2.5 volts, we consider this to be logic low. Okay, so in that case, we see that we get a truth table. So if we write this truth table here, this basically becomes, when V1 is basically low and V2 is also low, so logic 0 and logic 0, then the output is logic 0. When V1 is 5 volts and V2 is 0 volts, that is V1 is high and V2 is basically low, then the output V0 is 4.3 volts, and 4.3 volts would be considered as high. So when V1 is high, V1 is 1, V2 is 0, then the output is basically high, so 1 here. Okay, in the next case, when V1 is low and V2 is high, the output is 4.3 volts, that is the output is high. Okay, so in this case also, when V1 is basically 0 and V2 is high, which is 1, the output is actually high, which is 1. And in the fourth case, when V1 is high and V2 is high, the output is 4.3 volts, which is basically high. So when V1 is logic 1, V2 is also logic 1, then the output is also logic 1. So this truth table basically resembles that of a OR gate actually. When any one of V1 or V2 is high, then the output is basically high. Okay, so this truth table is that of a OR gate or OR logic. Okay, because I again repeat that when any one of V1 or V2 or both V1 and V2 is high, then the output is high. If both V1 and V2 are low, then the output is low. So this truth table corresponds to that of a OR logic gate. So this is basically an OR gate here. Okay. Similarly, let us consider another circuit. We have this diode here, D1. Here we have applied the voltage V1. We have another diode here, D2. Here again we have applied this voltage V2. And these are basically tied to the voltage. So this is 5 volts over here, and we take the output from this node. So this is a resistor R, and we take the output from this node basically. Okay. Now let us consider the different cases. So V1, V2 and V0. Now if V1 is at 5, let us consider the case where both are at 0 volts actually. So if V1 is basically at 0 volts and V2 is also at 0 volts, in this case both these diodes D1 and D2 are basically forward biased. Okay, because the voltage here is 5 volts, so the current would actually flow through both these diodes actually. Okay, so both these diode D1 and D2 are basically forward biased, and in this case, because in forward bias state the voltage drop across both D1 is V gamma and D2 is basically also V gamma. So basically, because we have applied 0 volts at this nodes, the voltage V0 basically would be equal to V gamma, which is basically 0.7 volts. Okay, because we have 0 volts here, and then there is V gamma drop across this diode D1, so voltage at this node must be equal to V gamma. Okay, so 0 volts, 0 volts, and here we have 0.7 volts, which is V gamma basically. Okay, now let us consider another scenario where V1 is basically 5 volts and V2 is actually basically 0 volts. So we have 5 volts here and we have 0 volts here. Now in this case, there is no current flow through this diode D1, because at both the terminals, here we have 5 volts and here also we have 5 volts. So there is no current flow across this diode D1, but this diode D2 is basically in a conducting state. Okay, so since this diode D2 is in a conducting state, in that case, the voltage drop across this diode D2 is basically V gamma, and so the voltage at this node over here should be equal to V gamma. Okay, so if V1 is 5 volts and V2 is 0 volts, in that case, because this diode D2 is forward biased, the voltage drop across this diode D2 cannot exceed V gamma. So the voltage at this node over here must also be equal to V gamma. Okay, so V0 is basically 0.7 volts over here. Okay, now in the third case, where this voltage 5 volts is applied at this V2 terminal, so we have 5 volts over here and V1 is at 0 volts. In this case, this diode D2 is basically not in a conducting state, because we have applied 5 volts here and we have applied 5 volts to this terminal also. So across both the terminal there is 5 volts. So this diode D2 must not be in a conducting state. On the other hand, this diode D1 is basically in a conducting state. Okay, because we have applied 5 volts over here and there is 0 volts over here. So D1 must be in a conducting state. And because D1 is in a conducting state, the voltage drop across D1 cannot actually exceed V gamma. So the voltage drop across D1 is V gamma here, and here we have applied 0 volts. So at the output node, the voltage must be equal to V gamma. Okay, so if we apply 0 volts at V1 and 5 volts at V2, then the voltage at the output is equal to V gamma. So 0 volts here and 5 volts here, the output voltage is 0.7 volts, which is V gamma basically. Now the fourth case is when both V1 and V2 are basically at 5 volts. So if both V1 and V2 are at 5 volts, then just as I stated before, that there can be no current through this diode D1 because the voltage here is 5 volts and the voltage at this terminal is also 5 volts. So D1 is not in a conducting state. Similarly, since the voltage at this terminal is 5 volts, D2 would also not be in a conducting state. So no current flow would actually occur across D1 or D2, so which basically means that there is no current flow through this resistor R. And if there is no current flow across this resistor R, then the voltage at this node must be equal to 5 volts. Okay, because there is no potential drop across this resistor R. Okay, so the output voltage must be equal to 5 volts here. Okay, so if we construct the truth table and considering the same logic as before, that for the voltage less than 2.5 volts is considered as logic low and voltage greater than 2.5 volts is considered as a logic high. So if we consider that logic and construct the truth table, we would get logic low in V1, low in V2 and also low in V0. And then the second statement here, which is basically high in V1, low in V2, this gives us low in V0. And then the third statement here, which is basically low in V1 and high in V2, this also gives me logic 0. And then the fourth statement is high in V1, high in V2, and then this gives us logic high at the output. So this truth table corresponds to that of a AND gate. So this is basically an AND gate. Okay, so this is how you construct OR logic gate and AND logic gate. And unfortunately, you cannot actually construct NOT gate with the help of diodes. So let me document it here. We can't construct NOT gates with the help of diode. And to construct NOT gates, we actually need something which is known as transistors. So the next topic that we would be studying is basically transistors, and you can actually construct NOT gate, NAND gate, and these kind of gates with the help of transistors. But diode can give you only AND logic and OR logic gates. Okay, so this class is up to here. And this is basically the end of our diode circuits, and in the next class we will be studying transistors. Okay, thank you everyone.